So the pressure of gases has a big effect on our weather as well. High pressure is usually associated with clear weather, and low pressure is usually associated with unstable weather. So having different pressures in the atmosphere creates wind, where the air will move from the higher pressure to the lower pressure. And it also causes change in the weather. And so when you see meteorologists showing things like this, they're talking about here's a low pressure front and here's a high pressure front. And that is related to the direction and the type of weather that we see. So we can see some variations in pressure, atmospheric pressure, due to the weather. And like we have a little weather station here, and it currently says that the atmospheric pressure is 29.43 inches of mercury, which is a little below 1 atmosphere. 29.92 would be exactly 1 atmosphere. So we say, when you're breathing that the external pressure is constant. It's relatively constant. It does change a little bit, but not a lot. If you go to a higher altitude, though, you'll also experience pressure changes. The pressure decreases with increasing altitude. So here we're looking at 2 mason jars with pink gases in them. So this would be a lower pressure, and this would be a higher pressure. This is a lower density or a lower concentration of gas, and this is a higher density or higher concentration of gas. So these particles are moving. You have more particles in that small container. They're going to collide more frequently, and you're going to get more pressure. Here with fewer particles, there'll be less pressure. Any questions yet? One of the things that happens if you go to a higher altitude, maybe you drive up 180 to see Grant Grove, your ears will pop, right? And then when you come back down, they need to pop too, or everything starts to sound kind of funny. So what's going on there? Well, this is difference in pressure of the atmospheric pressure versus the pressure inside your ear. So here's an illustration of your ear. This is your outer ear. And there's a membrane here called your eardrum. So the eardrum separates the inside of your ear from the middle and external ear. And that is impervious to water, to air. It's completely sealed off there. But there's an opening in here that does contain air, and that is connected via the eustachian tube down into your throat. So what happens as you go up in altitude, the external pressure becomes reduced. The internal pressure inside your ear is the same as it was before you started traveling up. And so you get this increased pressure in your ear, causing the eardrum to bulge out a little bit. And then at some point, your ear pops, right? It's not actually your eardrum rupturing. It's that sudden release of pressure as your eustachian tube opens up and allows the pressure to equalize. And then the reverse happens on the way down. You got your inner ear all used to being up at 7,000 feet or whatever. And so you've got low pressure here. And as you come down the mountain, you get high pressure out here. So the eardrum bulges the other way. And then you need to get your ears to pop and let air back in. Personally, I find that that's more difficult to get the air to come back in. And this movement of your eardrum based on the difference in pressures is probably the main reason that babies scream so much on airplanes, because their eustachian tubes are very small and it's much harder for their ears to pop. And especially if they have any sort of a head cold or congestion or, heaven forbid, an ear infection, it hurts a lot. So, any questions? What can you do to help your ears pop? chew gum or yawn or smash. Yeah, push your ears. When you chew gum or when you yawn, you're moving this area in your neck, and that helps it to open up. How do we measure pressure? This is the original method of measuring pressure. It's called the Mercury Barometer. Barometer is an instrument that measures atmospheric pressure. So the way this thing works is you have a tube, a glass tube here. It's very long. It has to be more than 30 inches tall. You fill it with mercury, and then you invert it into a dish of mercury. A little bit of the mercury will come out into the dish, but we've got a balance here between atmospheric pressure pushing down on the liquid on the outside and gravity pulling the mercury down on the inside. What we have up here is not air, but a vacuum. If we do this with water, try it at home with a cup of water, invert the cup in a sink full of water and then bring it up, and you'll see that none of the water comes out until the edge of the cup comes out of the water. Then it'll all come out. That's because water is much less dense than mercury. If we wanted to make a barometer like this with water, it would need to be like 30 feet tall. So that's why they use mercury, because it makes it a more reasonable size. 29 inches is still a pretty long thing. It's not something you're going to be able to keep in your pocket. So a guy named Torricelli was the one who developed this instrument, and he found that if you take this thing and you walk up the hill to higher altitudes, the column of mercury gets shorter. And then when you come back down, the column of mercury goes back up to where it was. And so you can measure pressure by measuring how tall the column of mercury is. And that's why we have this very strange unit, millimeter of mercury. It's literally the height of the mercury column measured in millimeters. Or like the weather people usually use inches of mercury, right? So higher pressure means the column is higher. Well, that's kind of a weird unit. So they created another unit called the torr, and the torr is exactly the same as a millimeter of mercury. It's just a fancier sounding name. Unfortunately, we're still using both of these, so it didn't really simplify anything. There are a number of different pressure units. The ones that are important to us will be atmospheres, torr or inches of mercury, occasionally inches of mercury. The Pascal is the SI unit. Don't run into that very much. PSI is what you see on your bike tire or your car tires. That means pounds per square inch. So 1 atmosphere, which is atmospheric pressure at sea level, is exactly equal to 760 torr. It's defined that way. That would also be 760 millimeters of mercury. So 1 atmosphere is 760 torr. 1 atmosphere is also 29.92 inches, 14.7 psi, or 101,325 pascals. So we can do pressure conversions in one step because all of these things are equal to each other. And so you just choose the unit that you have and the unit that you want, and you've got your conversion factor. This is how those conversion factors would be given to you, say on an exam. You'll be able to do problems a lot faster if you memorize the 760. 760 torr, 760 millimeters of mercury, that's 1 atmosphere. You don't need to memorize the rest of these. There's not really any point. But let's do this example. Your local weather report announces that the barometric pressure is 30.44 inches of mercury. Convert this pressure to PSI. This is just dimensional analysis. So we're starting with 30.44 inches of mercury. And we can always do these in one step. So I want to find pressure in PSI. And so I'm going to divide by the unit that I have, inches of mercury. Then I go to the table and I see, well, how are those related? Well, 29.92 inches of mercury is equal to 14.7 PSI. Inches of mercury cancel out. Oops. 30.44 times 14.7 divided by 29.92. 14.95548. Here we're going to be limited by this 14.7. So we would call that 15.0 PSI. Any questions? I could also convert, say, 820 torr to pascals. I'm trying to convert torr to pascals. I put pascal on the top and torr on the bottom, so those cancel out. And then I go and I look at the relationships here. All of these things are equal to 1 atmosphere. They are all equal to one another. So that means that 760 torr is equal to this many pascals. And we end up with this really big number. Which, yeah, I wasn't very nice with my sig figs there. I guess we could call this 110,000 pascals. Yes?
Our paper has all these for
For an exam, yes, you'll be given all of those. Yep. Any other questions? If you want to measure the pressure of a gas inside of a container, you don't use a barometer, you use a manometer. And mercury manometers work on a similar principle to mercury barometers. So here what we have is a U-shaped tube containing mercury. If this tube was open to the atmosphere on both sides, what could we say about the level of mercury on each side? Would one side be higher than the other if the tube was open on both sides? No. It'd be the same, right? You fill a tube of water, a big J tube of water, a U tube of water, and the level's on the same on the both sides, right? Unless you blow down on it or suck up on it on one side or the other. Well, here we have one side of this tube connected to a container that has a high pressure gas. So this gas is pushing down on the mercury on this side. And atmospheric pressure is pushing down on that side. Here, this side is higher, meaning that the atmospheric pressure is lower than the pressure inside the container. So again, we can measure the difference between the mercury columns in millimeters of mercury and find the pressure difference. That's not giving us the pressure inside here, that's giving us the difference between outside and inside. So we would have to take atmospheric pressure and add this difference to get the pressure inside. Any questions? Of course, now we use, just fancy electronic gauges to measure pressure.